Hey Norm, how are you?
Well, and yourself.
Good. So we'll just wait a couple more minutes as we see.
Usually wait until like right after, or maybe two.
Yeah, a couple minutes after, yeah. Is it kind of crummy?
I think it's a bit clarity.
The clarity.
Can you turn the lights on?
Yeah, maybe the lights would just be the thing. Yeah, that's good.
Yeah.
Well, you're in here, as you know. You're the next slide. I owe you a certificate.
Oh, of what?
So your SSL works on your website.
Oh, yes. A certificate of friendship.
Like usual for me, real hard to stay within 50 minutes, but I will do my best.
I mean, I don't have class till 2, so I'm fine.
Okay.
And I don't know that people in the case study. You don't see the audience get fidgety.
All right. In the way?
Pre-merger days.
Oh,
You were saying the people were gonna sort of just do a little thing about themselves. That's where I learned about hungry programmers. And then nobody else at NAN had time to say.
oh yeah. Right. Yeah.
It was-
I overspoke.
But
Yeah,
it was a
for sure.
super interesting presentation and I learned a lot of stuff. So it was really good. Well.
Runs found.
That could be the name of the consulting group you spin off.
Brunsfeld?
No, Hungry Programs. Do you still own that domain?
Yeah, hungry.com. Yeah. We all kind of co-own it. We've got offers up to a few $100,000 for it. But
I was gonna say.
yeah, it was back in the day when it was easy to get domains.
Hungry.com.
Yeah.
I could, that's worth money.
Yeah, we've had some offers, but we'd have to split it like 25 ways. So it's like, it just never.
We have Ellie.
I don't know.
Okay. Okay.
Evan
Uh-huh.
and David.
I think EPSCoR sent out a thing so that
Great.
other places would.
Well, we're reporting too. So. You want to start right on time and let the stragglers come in?
Well, if that's the case, you're late. Yeah, it's time.
Yeah. Yeah.
Do you want to go ahead?
I'd like to do the introduction. This is going to be great. I don't want to overhype it, but it's probably going to be the best thing that happens to you this year. So we have Dr. Luke Sheneman, who's the Director of Research Computing and Data Services here at the U of I. And I'm super excited because he's going to talk about generative artificial intelligence, but in particular, multimodal generative artificial intelligence. And I'm not certain, but I believe there will be themes of like eldritch terror and all sorts of crazy stuff in this talk, in addition to all the engineering and learning and science and junk, right? So yeah, all right, take it away, Luke.
All right, thanks, Barry. Yeah, okay, so I'm Luke Sheneman, Director of Research Computing. Excited to talk about multimodal AI. It's something that I think is super interesting and has been like a hot area right now in AI. And so I had this really interesting multimodal week this week, right? So number one, Anthropic, which makes the Claude AI system, large language model, released this new thing that allows their model to directly control your computer. And it does it in a multimodal way by taking screenshots constantly of your computer and moving cursors and typing and taking full control of your machine to do whatever it is you tell it to do with natural language. The other thing that I had fun with this week was there's a company called Minimax in China that made available this really awesome text to video model that I've been playing with. Now, there's a few of those out there. OpenAI Sora is one of them that's not quite out there yet, but there's a few others. But this one's free to use right now if you want to go and like Google it. So I took Barry's like picture from the web and animated him in all sorts of cool ways. I got him to do a high five with Sam Altman. It's a really, really cool.
Real.
The high 25.
Yeah, yeah. What's that?
High 25.
The high 25. Yeah, yeah. So anyway, you should play with it. It's free for 3 days. You get 3 days of free use, and it's really fun. So, and we'll talk a little bit more about some of that. All of that reminds me of this really awesome meme from 2021, which this Alex Bleckman says, okay, sci-fi author, in my book, I invented the torment nexus as a cautionary tale. Tech company, at long last, we've created the torment nexus from classic sci-fi novel, Don't Create the Torment Nexus. And so I feel like that's kind of where we're at, right? You've seen all of this amazing, scary AI sci-fi about computers taking control of things and whatever. And it seems like we're, with Claude's announcement this week, like we're kind of like inching our way there. Anyway, I wanted to open up with some humor. But so Barry mentioned generative AI. A lot of what I'm going to be talking about is generative AI. Not all of it. You don't have to be generative to be multimodal. But generative AI is definitely making big splashes right now, obviously. So OpenAI, Microsoft, Amazon, even Apple is getting into it, right? There's tons of companies out there right now that are investing huge amounts of money to create generative AI. And I will talk more about what generative AI actually means. But with that, you can do things that are multimodal. For example, convert text prompts to videos. In the case of Sora, you can make an entire 1 minute long video at 4K resolution at 30 frames a second with just a really simple text prompt. Same with Minimax, like I showed you, and others. The woman over here on the right, she's not real. That's a person that was rendered from a system called Midjourney using text. You can make music. You can do all sorts of things. You can even do science. So an example of generative AI in science is AlphaFold out of Google, which is a transformer-based system, and I'll talk about transformers in a minute, that takes as input amino acid sequences, uses the transformer architecture, and as output uses a different modality for output, which is 3D structures. Okay, so it predicts 3D structures based on sequence data. So let's define some terms here real quick. So unimodal is really simple. So the old version of GPT used to be unimodal. You input text, you get out text. Or there's a lot of unimodal image models. So SRGAN, or it just stands for Super Resolution Generative Adversarial Network, takes a small image and converts it to a large image. So that's an example of a unimodal AI model. Then you can have pseudo-multimodal. So pseudo-multimodal is kind of what GPT-4 was, right? So it was a large language model at the core that read text and output text. But it had a whole suite of helper models that could do things like translate speech to text, or take an image and convert it to a caption and then feed it in. And then on the output side, output through another model called DALL-E, or a text-to-speech model called TTS. So it's like an ensemble of models that all sort of work together collectively, and it's pseudo-multimodal. Then you can be native multimodal, which is your model takes as input one mode, like text, and outputs another one, like images, or takes an image and outputs a caption. So those are native multimodal. The frontier right now is native multimodality with lots of modalities, where you can input modalities like text, speech, images, video, music, audio, whatever, as input, and it natively understands the meaning of those different modalities, and it understands the relationship between the modalities, and can output potentially multiple modalities without calling external models. All of it's intrinsic in the one big transformer network. And so I'll be talking a lot about that. And examples of that right now would be GPT-4o and Gemini. And in fact, if you look at the current frontier models, you'll see that GPT-4o can handle text, images, speech, and audio natively, right? So that's a big change. So it can understand human speech without any other models in front of it or behind it. And so and it gets to the point now that it not only can understand what you're saying, but it understands the emotion with which you're saying it, and it can emit emotion to correspond to that. Gemini probably wins right now in the multimodality battle just because it handles, it can actually intrinsically do video right now where the other models can't. Claude can do text and images, and they claim charts and graphs are their specialty, and so they consider that another modality. I think it's just another version of images. And then open weights models like Llama 3.2, which just came out, are also now multimodal. It can handle text and images. But like I said, you don't have to be generative. So in healthcare right now, multimodality is a really hot topic. And so being able to take, for example, this is from a relatively recent paper, I think from this year, and that's the title of the paper, being able to take data like tabular data having to do with patient history, being able to take time series data like laboratory results, procedures, heart rate, blood pressure, respiratory rates, all of that, text having to do with patient records and test results, and then medical imagery, biomedical imagery, convert those into what we're going to call embeddings, and I'll talk a lot about embeddings, and then be able to reason and meaningfully use those embeddings, which is sort of an internal representation of those different modalities in a common latent space and in a common embedding space. And then from that, be able to make predictions or diagnoses or suggestions to the patient about lifestyle changes, all of that. So this multimodality is not necessarily generative, but it can be the precursor to like predictive modeling. Okay, so one of the cool things is that multimodality, and by the way, I've been playing with this new text to image system called Flux. And so almost all the images you see, I generated with this open source model here called Flux. But multimodality means has a lot of advantages over unimodality. So you're able, obviously, to integrate multiple data types, but that allows you to have a deeper, richer semantic understanding of reality, right? And so you're able to leverage complementary data across modalities, and because of that, you're able to fill in gaps. So there might be gaps in the text description, but that's filled in with an image or with some audio. And as a whole, you're able to develop a model that is actually better than training just under one modality. You're able to generalize better. You're able to develop a world model a little bit more effectively, so that even if you train with multimodality, but then when you just use it with, say, text, it's going to perform better because it has trained on more data, basically. So there are advantages to doing this, and one of the reasons why the big companies are going so eager to go into multimodality is because they've run out of text data to train on. So now they're switching to video, they're switching to audio, movies, eventually robotics, where you're going to have an infinite stream of novel data coming in through sensors and images through robots. So a little bit of a technical primer here. So just really basic stuff. You probably, if you've ever been to any of my presentations, you've seen this slide or some version of it, but neural networks. So these multimodal networks are neural networks. And what I mean by that is that you have the classic version of a neural network is what you see above, where you have an input layer on one side, an output layer on another. These layers are comprised of neurons, and the neurons are connected to each other. Now, this is an attempt to sort of model what happens in the actual nervous system or the brain. But the idea is that this is a fully connected network in which all of the neurons in one layer are connected to all of the neurons in the prior and the subsequent layer. And what you do is you have parameters associated with that model. So here you have two neurons that are connected to another neuron with these edges. Each edge has a weight associated with it. and every neuron has another trainable parameter called a bias. And so these weights and biases are trainable parameters that you tweak through a process called gradient descent, which is a method for sort of traversing a loss landscape, a highly dimensional loss landscape, to optimize a function. And you're trying to change your parameters by tweaking your weights and models as you pass data through this and evaluate how well it's doing. You tweak the parameters to try to optimize those weights for some purpose. And what it could be predicting the next token, it could be generating an image, it could be predicting whether this is a dog or a cat, right? It just depends on your use case. And because those neurons are organized in layers, these layers have sort of a role. Every hidden layer in the middle, which is not an input or output layer, they're called a hidden layer, handles a different level of abstraction, right? And so in the first hidden layer, you might imagine that it's able to aggregate features from, say, an image. And in this case, it's facial recognition. It starts to see edges and light spots and dark spots. It kind of starts to assemble these features at that layer. In the next layer, you're taking those features and starting to aggregate them into maybe ears and eyes and noses. So this next level of abstraction or composition. And then by the last hidden layer over here, you have full facial structures. And so you can start to do image recognition. And so transformers that are the basis of large language models and of all these multimodal models do exactly the same thing. They have repetitive layers that are able to extract ever more abstract composite features. So there's two sort of modes to these models, right? There's training, which is where you pass lots and lots of data through the model, evaluate how well your whatever task it is you're trying to optimize does on the current data, and then tweak the weights and biases in your model, and then and eventually you stop, right? Either your model is performing really well, or you just run out of time, or whatever. You stop, and then that is your trained model. Then you can perform inference with your trained model. You can pass it new data and have it do something. And hopefully it does it well. In this case, we're sending a picture of an animal and it's predicting that it's a cat, right? So that's really straightforward, training versus inference. And I will say, these networks that I'm showing here are trivial. The networks that are behind the large language models have trillions of these weights and biases, right? So it's incredibly large, complex networks. So generative AI, one definition that I like to use is that what you're doing with generative AI, when you train it, is you're learning a really highly dimensional representation of your training data, right? You're understanding how your training data is correlated to other parts of the training data in this really complex data distribution, this distribution, it's this statistical distribution. And then you sample from that distribution to generate an image or to generate the next token or whatever. But the first thing you do is train it, and then at inference, you sample from it, right? And so you can do that if you learn the sort of distribution of what it is to be a human face, then you can sample from that to generate very realistic human faces. And same thing with next token prediction. And so really, again, what you're doing is you're taking these different modalities and you're passing them through a part of your network that we call an encoder that creates this compressed latent representation, which is that statistical distribution in sort of a compressed form that you then can decode into modes or modalities that humans can consume, right? You cannot have a generative AI model without a decoder. Okay, a decoder is essential to bring it into a mode like text, images, video, audio that humans can consume. And there is no generative AI without a decoder. And in fact, ChatGPT is a decoder-only transformer network. I'm actually going to maybe skip that slide. So I'm going to talk just a little bit about transformers. So transformers were a thing that came out of Google back in 2017, and there was a paper called "Attention is All You Need." This paper sort of changed the landscape of large language models and a lot of other things, multimodal models, and I'll talk about that in a second. But this paper was originally written with the intent of a translation exercise. They were translating English to German and English to French. And they got really competitive results with this. And the current AI explosion that you're seeing right now is a direct result of this paper, which I don't think they predicted. They didn't know what they were getting into. And so why is it called a transformer? Well, really simply, if you have a language model, what it does is it takes the set of, in this case, words, we'll call them words, or tokens. You compute an embedding, and I'll talk more about what that is. Then you pass it through your transformer. It uses a mechanism called self-attention, where all of the tokens or words look at all of the other tokens and words in sort of the context of the sequence that you provided, and all of the stuff that it learned when it was pre-training. Then it outputs a different set of embeddings. So you have these embeddings, you get a transformed set of embeddings. These embeddings represent the semantic meaning of those words. And they get transformed when you look at the context of how those words are used in your sequence. And now you have a transformed set of embeddings. And we'll talk, embeddings are the key to AI these days and the key to multimodal AI. So it's really important to, yeah, go on.
Sorry, if we go back.
Yeah.
You said that on the left-hand side, the fish lived in that, those are tokens.
Yeah.
So did you just put word embeddings up there to connect to the words?
Yeah, it'll be a little bit more clear in the future, but yeah, you take these words and you turn them into a series of numbers called embeddings.
The words are a token.
The words are a token,
So
yeah.
So up top where it says word embeddings,
Mhm.
it should be token embeddings.
Yeah, I am using word and token interchangeably.
Gotcha.
Yeah, yeah. One of the amazing things about transformers is what is known as the transformer scaling laws. So this was a property that was discovered both by OpenAI and Google, which found that that this transformer model improves predictably, amazingly predictably, as a function of the amount of data you give it and the number of parameters in your model. So if you can scale the amount of compute or the number of parameters in your model, and you can scale the data, you can predict exactly how much these neural networks are going to improve. Traditional neural networks before the transformer didn't have this property. They would improve to some point and then they would plateau. Adding more data or more parameters wouldn't help. With the transformer, however, they seem to have this property that it will improve predictably as you add data and compute. And in fact, they've calculated that for every new parameter or weight in your neural network that you add, you need to add 20 tokens to your input data. Like, they've got it nailed down to that level of detail. And by the way, this is the reason why Google and Microsoft, OpenAI, Elon Musk are all investing in $100 billion data centers, because they want to add the compute necessary to get better and better and better performance. And this is why Microsoft now is kickstarting 3 Mile Island nuclear reactor again to power its data centers. It's this transformer scaling law that's doing that. So transformers only work on sequential data. So the data that you provide, it has to be linearly sequential. That it's really important. But it turns out that you can convert most data types into some serialized version that a transformer can work on. It uses this new method called attention, and it's very fast to train. It's very parallelizable. And because of that parallelizable part, you can use lots of graphics processing units or GPUs in these large data centers and get these things to, you know, create models in months where it would take literally years on a single computer. In fact, GPT-3, when it was trained, used something like 330 GPU years of training on a V100 GPU, which meant it would have taken over 300 years to train on a single GPU, but you can parallelize it over thousands, tens of thousands, or hundreds of thousands of GPUs, and get this done in a reasonable amount of time. But transformers, and especially transformer-based LLMs, are just functions. They're literally just functions which take as input a sequence and produce a token, one token. That's all they do. It's a function, input, output. So in this case, my input is the robots want to eat. I pass that into my function, and I get me as the result, right? And so with these commercial AI firms, when you use like their API to programmatically interact with them, you're literally just paying by how many times you call this function. Because calling this function is expensive. It takes resources, so you have to pay for it. But that's all a large language model is. But then you put it in a loop, right? And you call it, then you can call it autoregressive. And so what that means is you look at your current sequence, you give it to the transformer, it predicts the next token. You take that token and you add it to the end of your sequence. Now your sequence is a little bit longer. Then you call the function again and again and again. And until you get to a stopping point. Either you reach some sort of limit of number of output tokens you're allowed to produce, or the large language model can emit a special token that just says, stop, right? I'm done now. We don't need to go further. So it sounds like simplistic and mechanistic, and it really, really is, but it's really powerful too. Okay, now we're going to get into embeddings. So an embedding is where you take your token and really with large language models, you use subwords, not words, but we don't, since we're going deep into large language models, it's okay. We convert that into a number, which is just a lookup, right? This token ID is just an index number. It's a lookup. And then from there, we can tie that into a table which represents our token embeddings. So every token in our dictionary has associated with it a vector or a list of floating point numbers that is very long. Here I'm only showing 3 numbers. In reality, there are tens of thousands of dimensions or floating point values long. These numbers represent the meaning of this token. And the meaning is determined as it's pre-trained on your giant corpus of text, and it's determined by how tokens sort of co-occur in your training data. So you have these token embeddings, and these embeddings are going to be important when we talk about images, music, video later, but it's easier to think of it in terms of language. Now, even though it's just a series of numbers, it's a vector, but it's better to think of it as a vector in the sense of physics, where you have a magnitude and a direction. And because of that, you can think of your words like this, where you can map say your vector was only 2 dimensions instead of say 12,000, which they really are. You only have 2 dimensions, and we're going to name them gender and age, right? We're going to give them explicit names. Then you can see you can put tokens or words on, you can plot these vectors out and know that child and infant are pretty close together, right? The angle between them is relatively small. But grandfather and man are pretty close together, but grandfather and girl, oh, that's far apart, right? So that angle between them is far apart. And so you can actually use linear algebra, use dot product to compute the angle between vectors. So you can compute the angle between these token meanings. Large language models are built up, like I mentioned before, with that really simple, fully connected network. They're built up of many layers. GPT-3 had 96 layers. GPT-4, who knows? They won't tell. But the idea, right, is that you have your words. You look up your word embeddings that you learned during pre-training. You run those through your transformer when you're predicting the next token. And every possible token for this embedding is going to have a probability associated with it. So if I want to know what the next token on the sequence is going to be, I want to look at this last embedding, and I'm going to then map it to via probabilities to my tokens. And so in this particular case, the fish lived in the sea would be the most probable answer. And so that's what I would do if I was predicting the next token. I can change the temperature of my model by increasing it a little bit. That's a hyperparameter that you can set. And now it will not necessarily pick the top choice, but maybe the second choice at some frequency. And that's how these models can be created. You can increase their temperature. They don't always take this deterministic path. They can kind of take a little bit of a stochastic path. Okay, so self-attention, like I mentioned, all the tokens talk to all the other tokens. And I know I'm focusing a lot on language, but it translates really well over to images. And so it is a very expensive operation in the sense that it's n squared. Every token in your sequence has to compare itself to every other token in your sequence every time you want to predict the next token. This self-attention mechanism is really pretty simple once you've took me a while to wrap my mind around it, but it's actually relatively simple, where you have a particular word embedding. And what you do is you run that through a weight matrix that represents this question. What am I looking for? And you compare it against the keys from all of the other, the key vectors that get calculated from going up through this key vector. You compare using dot products. So you basically compare the angle, the semantic angle between your token and every other token in the sequence. And you're getting these weights. These are scores. These scores then get applied to the value. And so I'm going so fast because we don't have time to really dive into this, but I like to think of attention as a communication protocol in which the tokens talk to each other to determine what is the most important thing to pay attention to given the current context, right? And that mechanism, basically, at the end of this, you get your transformed tokens that are transformed and weighted depending on how they're used in the context of the overall sequence. And the reason why they use linear algebra, like weight matrices and things like that, and dot products, is because those are differentiable functions. And so your gradient descent for optimization can work with those. So it's actually really ingenious that they developed a communication protocol using linear algebra that can be used with gradient descent, and super exciting. So if you want to learn more about transformer-based large language models, I did a presentation last year, I think. There's a YouTube video on it, and I have a GitHub repository where I implement a really simple large language model that uses tokenization at the character level to learn Shakespeare, right? And then once it learns Shakespeare, it just spews Shakespeare. It's just a toy exercise, but it's only like 400 lines of Python code, but it's pretty cool. Okay, so now we're going to do a bit of a deep dive into a particular multimodal task, right? Which would be image and text, like when we combine those two modalities, right? So when you're combining those two modalities, there's a lot of possible tasks you could do, right? You could do image text matching, which is where you're trying to find text for images and vice versa. There's image captioning, where given an image, you want it to caption it. You want it to describe what's in the image in natural language. You could do visual question answering, so I can start asking questions of my picture and I can get answers in natural language out of that. You can do sentiment analysis, classification, all sorts of things. This is possible if you do true multimodality. And so, sentiment analysis is really simple. So this is a modified, this isn't really Barry's face. This is a modified version of Barry's face. And I asked, okay, what is this person feeling? And I actually ran this through, I think, GPT-4o, right? And so it did a sentiment analysis. It says he's skeptical, okay? And it went, I had to truncate this. It went into great detail about how Barry's feeling, right?
That's literally how I'm feeling all the time.
Yeah, okay, well, good. Yeah, and then I generated another image, and I just had it generate a caption. So I had one AI system develop an image, and then I had another one develop a caption, and again, I cut it off. If you read it, it's pretty darn good, right? Like, it knows what's happening in the scene. Not only the details, but like some of the background that's probably happening, and the feelings and emotions, and all of that is in there as well. I generated this kind of crazy image so I could ask questions about what's in it, and it did a great job, right? So this was all GPT-4o, which is multimodal, and it's got
West Coast bias.
What's that?
The West Coast bias.
West Coast bias?
The sunset sky.
Oh, okay, yeah, there you go. Yeah.
Obviously, they're in California.
Obviously, yeah. Okay, so I wanted to talk a little bit about this model from OpenAI called CLIP. So this came out, I think, 3 years ago, 2.5, 3 years ago. And it's one of the most powerful multimodal models that you probably never heard of, but it's actually under the hood for a lot of things. So the version 2, I think, of DALL-E was actually originally called UNCLIP. But CLIP is a model. CLIP stands for Contrastive Language Image Pre-training. So the idea is it was trained on 400 million text caption pairs. So you have 400 million pictures and 400 million captions, and it was trained on that. And so here's a picture. Here is a really short caption. the idea is that you use what's called an encoder to take the text and encode it into those embeddings that I was talking about before. And you do the same thing with the image. And I'll talk about how you compute embeddings for images in a minute. But you compute the embedding for the image. And as you're training it, you make sure, it's really simple algorithm, actually. You just make sure that your embeddings line up for the pictures that match the captions, and that you penalize it when you're looking at a picture and the wrong caption, right? So you're penalizing that, but rewarding it when they actually match. And after that, you have a model that understands and uses a shared embedding space, right? So your embeddings are the same for images and text. Now you can do a lot of powerful things since you're in this shared latent space, shared embedding space. But wait, so remember I said earlier that transformers only work on sequences and an image isn't really a sequence, right? But there was a paper that came out right around the time CLIP came out called, this is from Google DeepMind, called An Image is Worth 16 by 16 Words, Transformers for Image Recognition at Scale. And so they basically show that things like convolutional neural networks and other traditional model architectures aren't really necessary anymore. We can do everything with transformers. And they describe this process where they take an image and they carve it up into a bunch of small patches. And they use 16 by 16. That's why it's in the title of their thing. And that's a really common image patch size for a transformer or vision transformers. But they carve it up into a bunch of patches. They serialize them. And now we have a sequence. We have a sequence of patches. I will say you also have to include in your patches some signal in here about where it was in the image, X, Y, so that gets carried on to the model, but we won't have time to go into that. That's called positional encoding. So your patches are now tokens. Okay, cool, I have these patches. So assuming that I have 16 by 16 patches and a 512 by 512 image, I have a sequence length of now 1024. It's a decent size for a transformer to work on. Okay, but how do I compute the patch embeddings? Because I need to go from patches to embeddings, right? Tokens to embeddings. If in like language models, tokens are discrete, right? And you only have a vocabulary of 50,000 tokens. So the number of combinations that you have is such that you can actually have a fixed dictionary, like this discrete dictionary of tokens and their embeddings. With images, a single 16 pixel by 16 pixel image that's 3 layers deep, red, green, blue, has 2 to the 6,144 possible combinations, which is more than the particles in the universe, right? You can't have a dictionary for all the possible 16 by 16 patches. It's too impossible. So what you do instead is you learn a function. We call it a projection. You learn a function that can take a 16 by 16 red, green, blue patch. We serialize all of those pixels within it. And if you include the 3 channels, that's 768 individual values of positions. Then you run that through a linear projection or a nonlinear projection to get it to now project to something that is your embedding length, the same embedding length that you use for your language model, right? GPT-3 uses an embedding length of almost 13,000 dimensions. And so that's what we would do here is we would project from 768 through this fully connected neural network to a much larger embedding space. And now our images and our text use the same embedding length. And so what you do is you have your input image, you serialize the patches, you run those through your linear projection, and you apply your positional embeddings, which I mentioned earlier. And now you can start doing transformer stuff on it, right? If you want to learn more about vision transformers, I gave a talk last year on vision transformers, specifically just a toy exercise that uses vision transformers to classify dogs and cats. And so I have a YouTube video and a GitHub repository with my vision transformer there. And it was pretty cool. It worked really well. It was a neat exercise for sure. So, okay, so how do you get to that point where they have a shared embedding space? So again, let's take this example. So Joe Vandal with a lightsaber is my text. I have an image of Joe Vandal with a lightsaber. I run that through my text encoder to get my text token embeddings. I do the same thing with my image encoder, like I just described with the patches and the continuous projection. I get my embeddings here. I first do self-attention. So I basically just within the modality, within the image, I just start looking at how things are related, right? There's this first initial step of self-attention, and you do that for the text, you do that for the image. Then you take the transformed embeddings from that process, and you do what's called cross-attention. That's where the embeddings from the text are looking at the embeddings from the image as it does the full attention, the cross-attention. So now the text and the image embeddings are looking at each other as part of the transformer process to understand the context, the deeper context. They're sharing the same, they're now part of the same sequence effectively through that cross-attention. Okay, but that's great. So, but I bet we could add more than just captions to our multimodal model. So, okay, here's Joe Vandal. That's a really cool Joe Vandal with a lightsaber. You can use traditional computer vision methods like segmentation or object detection with bounding boxes, generate scene graphs, or generate question and answer pairs. If you can create all of those labels for your image, you can also incorporate that into your semantic understanding of what's happening in the image. So that not only do you know Joe Vandal has a lightsaber, you know that Joe Vandal's holding it with his right hand, and that it's red, and that he's in a misty forest, and that he has a helmet. Like you can do all of that if you apply these other computer vision methods to it without necessarily having that all in the caption. So I mentioned scene graph. So scene graphs are kind of cool. It's where you take objects that you detect. Yeah, go ahead.
The previous slide, the additional things you can do. Do you know which is cheaper, like putting this captions or this comparing cost-wise?
Cost-wise?
Or
I mean, cost-wise, yeah. So what I would do is all of the above to make the most powerful model, right? To some extent, what you get from a segmentation map and an object detection with bounding boxes is somewhat redundant. You get a little bit finer grained, with segmentation, you're basically outlining every pixel that belongs to an object, right? So you have very fine grained detail there. But since you're cutting it up into 16 by 16 patches, it might be overkill. So it just depends. But if you have the resources, the best thing to do is to label all of this and use it when you're training. So a scene graph, basically, there's models that do this, that will take an image, detect what's in it, and then create a graph structure, right? Which is, you can say, the woman who's in this bounding box has a helmet and has a boot and is riding a bike. So it's basically a relationship graph that describes a scene. This is used in like video games and other things where they're trying to do composite scenes. But there's models that will just take an image and generate a scene graph, right? And so that is a really powerful way of understanding, okay, this person is on top of this and they're doing this and whatever. Because if you've ever used these text to image models before and you've tried to get them to do specifically exactly what you want, they often won't, right? Because they weren't trained with enough of that level of detail. And so they don't understand it based just on their caption, right? They just can't, don't understand necessarily the Viking is holding the sword in the right hand, for example. And so trying to generate an image like that might be really problematic. So what would the training labels look like? Well, it would just look like something like this, right? Where you have, okay, this is just JSON, right? So here's your lightsaber, here's my caption, here are my bounding boxes and the labels associated with them. Here's my scene graph represented in JSON. Here's some metadata describing some other context with what's going on. Then I can actually input some questions like what's going on in the scene? What is the Viking holding? Where is the Viking standing? All of that. It seems like that would be really time consuming to create all these labels, right? Like, all of these different modalities of labels. Well, fortunately, we can now bootstrap that. There's AI models out there powerful enough, and some of them very specialized, that can do all of this for us, right? That can take a picture and generate all those labels that I just showed you. And so this is like a lot of the compute cycles that are being used right now for training large language models isn't necessarily just in the training, it's in all the stuff that happens before that, just getting the data into a form that will have enough rich training labels that are useful. Okay, so I'm going to talk a little bit about diffusion. So diffusion is how multimodal AI models today create images, but also videos and music, right? So it's a new, relatively new method. It's been out a few years now. And I'll go into some detail about how it works. And it's actually really, really cool. So in this case, we're doing with images. You have basically two main processes. You have a forward diffusion process and a reverse diffusion process. In the forward process, you start with an image, a pure, clean image, and you add a little bit of Gaussian noise, just a little bit of noise at multiple steps. And usually you go like 1,000 steps out. You just add a little bit more noise, a little bit more noise, a little bit more noise, until you get to just pure randomness. But what you do as you do that is you train a model to learn how to reverse that noise. Every step, it learns how to reverse that noise. Okay, so that when you're doing reverse diffusion, you literally start with a purely random image. And you use an AI model to predict what the noise is from that image and remove it, and remove it, and remove it, until you finally end up getting an image again that hopefully closely matches what you started with. So that's diffusion. But the cool thing about diffusion is you can now, if it's multimodal, you can condition what it produces based on text prompts, right? Again, you have to be in a shared latent space where your embeddings for your image match your embeddings for your text. And once you have that, as you're doing the reverse diffusion process, you're basically using what they call a semantic map to reward your denoising of the image from pure noise. You're denoising it slightly, and when you do that, it sees how closely aligned you are with the embedding for your prompt. And you try to maximize your adherence to your text prompt based on those embeddings. And it's super cool. So I made a diffusion model. I gave a little talk on it where I learned how to diffuse human faces. So this is a really simple thing. I didn't do any sort of text conditioning, but there is, I do have a GitHub repo and a YouTube video associated with it where I basically trained it on, I think, 5,000 celebrity faces. And then I just had it, starting with pure noise, generate me a face. And this is some examples of what it produced, which, aren't great, obviously, but you can tell they're human faces. And you can see that, my model wasn't terrific, but it was only trained on 5,000 images on an NVIDIA RTX 4090, whereas Stable Diffusion was trained on 600 million captioned images and took about $600,000.
How much did yours cost?
$1, I don't know, something like that. It was, yeah. It was just to learn how it works. Okay, so now we can translate this to video, and going from image diffusion to video, or for understanding images to understanding video, is just a matter of adding one more dimension, right? That's all you're doing. So video is just 3D data where you have images through time, right? And so what you can do is you can run that through an encoder that carves those up into space-time patches. So instead of just image patches, now you have small space-time patches. That might be 16 pixels by 16 pixels by, say, a quarter of a second of time, right? So now you have these little three-dimensional space-time patches. Then you just serialize them, compute the embeddings for those space-time patches, and now you have a set of embeddings that your transformer can work on. And so generative video diffusion is almost identical to image diffusion. So, so what I just described here is like, if you want to understand what's in a video, this is how you would do it. But you also can use a lot of the same principles to do the diffusion. So these are examples from OpenAI Sora, where, like I said, it can generate up to a minute of video. And it's almost identical to image diffusion, but uses these 3D space-time patches. And really what it does is it starts with a full minute of just static, right? And it denoises the whole thing all at once. It denoises it in steps, but it's not like it's denoising the first frame and then making the second frame, and then the third frame. It's denoising the whole thing across time stepwise, meaning from really noisy to no noise, all at once.
Does this selection of the noise first to start with matter?
Yes, so
So how does it select it?
well, usually it's just purely the random noise is just pure random, but that randomness will affect to some extent how exactly the scenes or the images will get rendered. Based if there might be a little bit more white over here, a little bit more dark over there, that's going to have an influence on your overall result. It'll be conditioned on this adherence to your semantic embeddings for your text prompt, but it will be affected. And that's one of the reasons why this is always stochastic. Like every time you run a diffusion model, you'll get a different answer because your random starting point was different.
To see.
What's that?
To see.
As a seed, yeah. So you denoise all the frames together at once. So that's super cool, right? Like it's sort of like you're not denoising across time, you're denoising across noise levels. And yeah. So again, what can you do with that? Right, you need to give lots of label data. And so giving label data to video is pretty straightforward, just a lot more of it, because now you have to define what's happening in every frame, or at least every key frame, like significant changes. So here, again, here's a description of, a Viking warrior clashes with enemies in the forest is the context. We have this whole set of repeating things, which are frames. So at frame 1, we have a Viking and a sword. Here's the bounding boxes of where they reside. Then in frame 45, we have an enemy and a shield, and so that kind of describes in text the events that are happening in text over what's happening in the image. You can have captions, the overall caption for what's happening in the movie changes. And then you can have scene graphs and questions about what happens and what timestamp in the video. So these JSON files that are often used for labeling video can be really huge, but again, they can be automatically generated by AI that can just analyze a video and generate this stuff. So one of the really crazy things is emotion. Human emotion can be captured in some of that semantic space, right? So there's just different dimensions in that highly multidimensional space. And so there was a recent Reddit post where somebody took this Minimax thing that I was playing with Barry's face with and got it to emit different emotions. And it was amazingly good at understanding the different emotional labels and generating. This, by the way, isn't even a real person to start with, right? This is a fake person having fake emotions. But man, it's compelling, right? Like it's crazy how good it is. When OpenAI announced their debacle with Scarlett Johansson's voice, they actually said, look, you're probably going to get emotionally attached to this voice thing because it actually understands your emotions and can respond emotionally in kind. It's just part of the semantic context, right? And in fact, there's a company called Hume that specializes. They have an empathic voice interface, or EVI, which is really close to the word evil. But it's a foundation model for speech that understands and can respond emotionally, right? And so that's their specialty. So anyway, that's what I have. Happy to answer any questions that you got. Sure.
For the attention mechanism that is doing that cross section.
The cross attention?
For the cross attention.
Mm-hmm.
That's similarly following that sort of like communication protocol that you were talking about earlier.
It is. Yeah. So self-attention is where you attend to just all the tokens in the same sequence, self-attention. Cross-attention is when you have two sequences and you're attending across them. And so in the case of the original transformer model, let me see if I can find that
So
one.
it's like, I've got the word token thing in one thing, I'm paying attention to the context over in the other sequence.
Yes.
I see.
And so in the original transformer model, they had an encoder and a decoder. And you can see that they actually do a form of cross attention. So they do an initial attention within the modality that's within this decoder, but then they bring in the embedded tokens, or yeah, the transformed tokens here and do cross attention on it. So you're attending your English and your German. You've got some, you've got some pre-computed stuff that you've done before with those embeddings before you do the cross attention. But then once you get to that point, you're really looking at your English embeddings versus your German embeddings, and you're looking at the context and how they're interrelated. And so it's the same thing with multimodality. Now what you're doing text embeddings versus image embeddings or video embeddings. Yeah.
When you described how the image recognition, or let's say training,
The labeling, yeah.
Does it seem to you, and you could look at that's when you add also the segmentation, the boundary boxes, and these other features, it started to make a little bit more sense. But prior to that, we talked about this before. Does it seem to you intuitively sort of improbable that we could serialize an image? It's not like language. Language has certain rules and forward in time, and some faculty rules are fairly constrained. Whereas images, it doesn't seem, I'm just responding emotionally here, that practical that you could take you could chunk up an image and put it on a string and have it.
Yeah, so when you do that, you add I didn't have time to cover it, but you have this thing called positional encoding.
Yeah.
So with even with just one-dimensional text, transformers don't really know, they do everything in parallel. They do that attention mechanism in parallel, and they don't necessarily think about the overall sequence position of a given token. They don't even know it. So you have to add to the embedding for that token a little bit of signal that tells it where it is in the sequence. And it transforms the meaning of the token slightly, but that's okay because the meaning of the token depends on its position in the sequence.
I mean, that's pretty much what I was getting at. It feels like we tend to sort of weight towards certain behaviors. For instance, in a portrait, the human is in the center of the image.
Yeah.
It's not on the edge, or just the idea that the visual space could be sort of
Serialized.
yeah.
I think based on what I've seen from how well these models do for both like understanding the contents of an image and then being able to generate them through diffusion, I think that it's okay to serialize images. I think they get it, that you have to give them that positional information. And with images, it's two-dimensional, right? So you have to tell it basically the XY of where that patch is in the sequence. And so that it knows what other patches it's nearby, like spatially, right? With video, you have to do it in three-dimensional encoding. So now it knows space and time.
Makes it an expert.
Yeah, and so I think it does pretty well. I think you can serialize these things, and there's probably, certainly there's bias in if you're learning images where people are always in the center of the picture. That's just a bias to your training data. Yeah.
So our language has embeddings and semantic coherence related to two-dimensional space, up and down, left and right, and that kind of thing. And so to me, it makes perfect sense that if you have a two-dimensional, or you have the XY thing as part of the embedding space, that can share an embedding space with language, because we have language to describe the top right quadrant of that image. Right? To me, it makes sense.
I think, yeah, I agree. I think, your choice of patch size matters a bit, right? So coarse patches versus small patches. 16 by 16 seems to be the common one. One of the things I should mention, if you're using like a semantic map like this, where you could actually have, within a 16 by 16 patch, you could actually have two classes represented in it. It's right at the intersection, somewhere, I don't know, between the glove and the sword or whatever, right? Like you can have that, and what they'll do is they'll weight it. They'll weight the amount of signal that they introduce to the embedding for that patch, for that particular class, depending, what percentage of this patch is glove versus what percentage of this patch is lightsaber. and they'll actually affect the embedding proportionally. If you're using semantic maps, you can do something similar right at the convergence of intersections of bounding boxes too.
If you go back to your linearization of pixels, the embeddings that you showed,
Oh,
function, enlarged function.
yeah, this one.
Yeah.
Yeah.
So it will also depend on, because there's a loss function, so some sort of a loss.
There's a loss function.
So-
Yeah. Right.
So it depends on how lossy the system is.
Uh-huh.
That will determine the approximation that you get and the semantics Barry was talking about.
Right.
Will come to close to actual thing, maybe. So long it is not that lossy.
Right.
That's what I think.
Right. Yeah, so all of the weights and biases in the entire vision transformer or diffusion model or large language model depend entirely on your task and how you measure loss. Because you're trying to optimize you're trying to lower your loss over time. And so every parameter gets tweaked as a result of that. And so your choice of loss function is super important.
And also how you compensate for those, all the other dimensions that you talked about,
Mhm.
like image relationships and segmentation.
Right,
So that can bring into more kind of a correctness to it.
exactly.
There's a question in chat from John Lee.
Okay.
Do you want me to read it?
Could you read it? I don't have it all.
Nice talk. How can such a model be used for agriculture and other real industry worlds?
Okay.
Yeah, that's a good question, how to use generative AI for science. I gave the example of like AlphaFold, which is a good example with protein folding. I mean, I suspect, we're working right now with one of the Gen AI fellows in our group that, so it's Jaslam, I can't remember his last name. He's working on understanding LiDAR data. And trying to basically do classical sort of segmentation of LiDAR data, but he doesn't have enough data to actually train a model. He doesn't have enough ground truth data to do it. And so we've talked about using generative methods like what I've talked about here to help generate synthetic data that he could then use to train other models. So that would be a case where in precision agriculture, or maybe you're doing some sort of aerial imagery or satellite imagery of ag fields or forests, you could use methods like that to help you synthesize new data that you could then train real models to work on real data. Yeah.
Are there any modalities that have proven, at least so far, to be particularly hard to serialize?
Not that I know of. I mean, the obvious ones that I didn't cover are like speech and music. Those are like obviously serial, right? Those are very easily like turned into sequences. One of the modalities that I think you're going to start seeing more of is tactile feedback for robotics, right? They're going to mix tactile inputs with visual and audio, imagery. I can't think of any modality that would be particularly problematic, but I mean, yeah. Either. Yeah. At first, before I wrapped my mind around how vision transformers worked, I'm like, how are you serializing an image in a way that's meaningful? And the way they did is pretty clever, with the patches and the patch embeddings and the positional encodings. And so it makes me think that you could do it for most things. Yeah. Did you have another question there?
Okay, but I can talk to you. So
Okay. All right. Okay. Well, thank you guys. Appreciate it.
Send emails with training that years already.
Okay.
And can solve what tables.
Okay.
I was trying not to bother you with this one.
Yeah.
Because we're going to change two things. One issue is that we need to let other people use or access the database from outside.
Okay.
Carlo told me that we cannot do that right now. Is it?